Hello everybody. Today's tutorial shows how to set the sensitivity calibration. This calibration should be realised after the velocity and the wedge delay calibration, but before the TCG calibration is performed. The purpose of this calibration is to level the signal response of the reflector for all the angles at the same reference level. To achieve this calibration, you are going to need a VEO Plus or Prisma instrument, a phased array probe and a reference block. We are still in the same setup as the previous calibration video, and we are going to select the sensitivity wizard. As a reference reflector, you can choose from 3 different kinds of geometry, either a radius, a thickness or a side drilled hole. For this calibration block, we will be using the radius geometry. To make the calibration easier, we suggest you put the signal amplitude slightly under the reference level. The next step is to set the extracting box dimensions, making sure that all the signal is within the box. Once the radius has been swept completely, we can easily see that some angles have higher responses than others. The reference is set at 80% and the tolerance at 5%, which is good because the signal response is already close to the value. Before recording the signal, or if a mistake occurs, we can reset the envelope before applying the sensitivity. Once the envelope has been recorded, we can apply the sensitivity gain correction to the signal. At this stage, we recommend you do a validation of the signal correction. We can now see that the signal for the 60-degree angle is slightly off tolerance. If this occurs, we need to sweep again the reference and reapply the sensitivity correction until the signal is within the expected tolerance. Once the wizard has been completely successful, we can confirm that the signal amplitude response is 80% for all angles once maximised. We hope this tutorial has been useful. Thank you for being with us. Hello everybody. Today's tutorial is about velocity and zero calibration. This calibration is setting the speed of sound value of the calibration block material and the appropriate delay 0 for the beam used in the calibration. For this calibration, you're going to need a VEO Plus or Prisma instrument, a phased array probe and a reference block. We are using the same setup as in the previous video and are going directly into the velocity and zero wizard. For the reference type, please select the specific radius to match your calibration block. make sure to enter the good value of the reference radius. On the screen, you should normally see 2 echoes from both reference radii. The manipulation for this calibration can be done with the block lying on its side. This configuration normally helps to stabilise the signal. For more accurate results, it is recommended to make the calibration with an unsaturated signal. Once both radii echoes appear, we can maximise them and record the maximum value within the envelope. If you make a mistake, use the clear envelope option and start again. Once the envelope has recorded the maximum signal response, adjust both gates over both reference radii echoes. Finally, click twice on the F3 button to go to the validation window. To confirm your velocity value, check the path measurement of both your gates in the A-scan. Always make sure that the calibration speed is close to the theoretical value of your material speed. Finally, the velocity calibration sign will turn green. We hope this tutorial has been useful. Thank you for being with us.
You may have heard of TFM, but what is TFMI? Let's check it out. With regular TFM, you've got a lot of modes to pick from, right? So you usually need to know a little bit about the type of flaw and the orientation of it before you pick the optimum mode to try to image that flaw. Just a few degrees of tilt or a few facets may cause a planar defect to disappear on some modes. This makes TFM challenging to use for detection. It's really easy to miss something if you pick the wrong mode. TFMI is intermodal TFM. This allows us to combine the information from multiple TFM propagation modes into one more coherent image. TFMI is something that I developed in cooperation with Sonatest over the last year or two. It's now available on the VEO 3. Now, intermodal or multimode TFM is not entirely new. It has been available on some software packages in the past, but this is the first time that it's been made available on a field portable instrument. We can combine up to 4 modes at once in real time. You can do that in combination with regular phased array or regular TFM. For the purposes of this, I'm just going to use 2T, 3T, 4T, and 5T for all these demonstrations. We'll test it on some simple targets. First, I'll use this Vermon NDT 10 MHz 64 element A12 transducer on this wedge, and we'll stand back a little bit from the targets just to pretend like we're on a real weld. Here I've got a stack of side drilled holes. On the left is TFMI and on the right is regular phased array. Those holes are really close to the surface, but at 10 MHz, the resolution is really nice. Then on the other side of the block, there's a porosity cluster, again, just some side drilled holes. There are 5 of them, and from this side, we can see 4 of them, and you can see the comparison between TFMI and phased array. Notches and holes are nice for a demonstration, but they're not real. So we'll get a little bit closer to reality, and we'll use this machined crack. Here, I'll push the probe towards the crack, and we'll show a comparison between TFMI, 2T, 3T, 4T, and 5T regular TFM modes, as well as phased array. Now, the top of that machine notch is 15 millimeters from the bottom surface. It's 25 millimeter thick part. So my cursor here lined up at 10 millimeters down from the top lines up really well for height sizing. Now that looked really good, especially comparing the TFMI to the regular TFM modes. But how does it perform on a real weld piece? Well, in this case, we're going to use a Flawtech 1-inch sample, and it has 3 flaws. It's got a root crack, a toe crack, and a sidewall occlusion. From the first side, using the same 2T, 3T, 4T, and 5T combination in TFMI, the root crack and the toe crack both image really well. In fact, if we zero in on that root crack in a different scan, you can see it follow the prep on the bottom, and then it moves up into that angled bevel face. And on the toe crack, it's less faceted than the root crack. Sizing is fairly simple, as the 4T signal dominates that intermodal combination, gives us a really good tip diffraction. We get about 4.6 millimeters for TFMI, which is the same as what we get for phased array. Again, no change to the setup. Looking at the lack of fusion from the opposite side, the fidelity on that is also really good. The whole point of TFMI is improved geometric fidelity. We can make a better picture of the thing we see in the weld. It's robust in that we can use the same combination of propagation modes to find a whole array of different flaw types in different parts of the weld. We cannot do that with regular TFM. It's really easy to miss things, and a better picture of the flaw makes a better report. I hope you found this video useful. If you did, please hit the like and subscribe buttons, and thanks for watching.
Hello everybody. Today's tutorial shows how to do a wedge delay calibration. In a typical workflow, this calibration usually occurs after the velocity calibration but before the sensitivity calibration. In the velocity and zero calibration, we settled the velocity for one angle only. The velocity of sound in an isotropic material remains constant for all angles. The zero, however, changes according to its related angle. This calibration wizard calibrates to zero for all angles. The same equipment as the velocity calibration is required. We are going to select the wedge delay wizard. It is possible to do the calibration on a different reflector, but for this block, the radius is the best one to use. As always, we will get better results with unsaturated signals. We suggest to put it around 80% full screen height. The signal should be within the extraction box border. We can now see that our reference is at 100 mil and that the tolerance by default is 2 mil. If you're unsatisfied with your wedge delay correction, it is possible to remove the envelope. Once the reference swept, the wedge delay correction can be applied. When the signal is within the required tolerance, we press F3 and accept the calibration. We can now see that the reflector is at 100 mil for all angles and that the wedge delay calibration indicator status is green. We hope this tutorial has been useful and thank you for being with us. Hello everybody. Today's tutorial explains how to do an automatic TCG curve using the TCG, DAC and DGS wizard. The TCG, or time corrected gain calibration, should be the last calibration that you set, since the others could affect the signal response of your configuration. The purpose of this calibration is to equalise the amplitude of the response from a reflector for all of the angles at different depths. This calibration is meant to counter the attenuation of the signal response of the sound propagation inside the material. For this calibration, you're going to need a VEO Plus or Prisma, a probe and cable, and a navship block or equivalent TCG block. We are using the same wizard principle as shown in earlier tutorials. In this example, we select a 2.25 meg probe and we add a 3D view to our inspection setup. As you can see, all the calibration markers are green and the TCG is the last calibration to be set. In the Calibration tab, we are going to select the TCG, DAC and DGS menu, and then the TCG as a reference curve, which is the most commonly used. There are three modes available to generate the curve. The automatic calibration will generate the TCG curve using the extraction box. This mode is usually faster, easier and more precise, so we're going to select this one. Once the type and mode of the curve have been selected, we are entered into the wizard manipulation section. You can change your general inspection parameters in the first step of the TCG wizard. In the next step, you can set your gain reference and curve amplitude reference with the Set Ref Gain and Ref Amplitude button. Make sure to maximise the reflector response before setting it as a reference. The next step is for the extraction box dimensions and desired depth jumps between reflectors. In our case, every reference reflector has a spacing of 6.25 mm. Once the extraction box parameters are set, we can sweep the first reflector of the TCG block. The red curve is the maximum amplitude response of the reflector within the extraction box for all of the angle beams. When all angles have passed the reflector, we can apply the TCG at the reflector. This will create a gain compensation on every angle beam to equalise the signal response. If we sweep again, we can see that the signal has been compensated, but it still is outside of the inspection tolerance. This step is an iterative process, which could require a few trials before reaching the required gain compensation. In case of bad manipulation, the gain compensation could worsen the signal. In this case, there is an option called Reset TCG Calibration, which cancels the gain correction. The coupling and the probe orientation between the wedge and the part are crucial parameters. If inconsistent, it will be necessary to repeat the process. It helps if you use a guide for your probe to ensure the probe and block orientation remain stable during the sweeping step. Once the signal is within the tolerance, we can do the next reflector. Now that the coupling and the probe relative positions are optimised, the second and third reflector should be easier. The second and third reflector only need one iteration to enter within the TCG curve tolerance. The last step is to validate the obtained curve. Every reflector on every angle should fall within the tolerance of 80% signal response. We should also see that every angle has a distinct TCG curve. Once completed, all the calibration markers will be green and the signal response for a given reflector would be the same regardless of its depth, distance from the wedge or the angle beam orientation. We hope this video has been useful. Thank you for being with us. Hello everybody. Today's tutorial shows how to connect your VEO Plus to an electronic device such as a computer or cell phone using the UT-Link software. The first step is to download and install the UT-Link app on your selected electronic device. To create the connection between both devices, the software needs an IP address and an associated password generated in VEO Plus. Once we have a connection, I will show you where to find this information. As you can see, I am now controlling the VEO Plus remotely from my computer. To find the required information, you first have to open a session. The IP address information is in the About window under the Network information. The remote access option must be turned on and its associated password must be known or changed. There are three ways to connect the VEO Plus with an electronic device. The first way is to share the same network using an Ethernet cable, as demonstrated here. If you do not have an Ethernet plug or cable, but you have a Wi-Fi connection, it is possible to connect the VEO Plus to a network using a Wi-Fi signal. Once you are into the Wi-Fi configuration page, which is under Connect to a Network, you can connect the VEO Plus to the same network as your computer. You will know when you have connected by the green check which appears next to the chosen network. If we now go back into the About window under the network information, since I didn't remove my Ethernet cable, the Ethernet IP information is still there and a new Wi-Fi IP address has been generated. This can now be used to connect the devices together. I am now going to demonstrate leaving this UT-Link session connected by Ethernet cable, and I'm going to create a new session using the IP address generated by the Wi-Fi connection. The new address generated ends with a 0.47 instead of a 0.45. As I didn't change my password, I just have to press on connect, and I'm now controlling my VEO Plus through the Wi-Fi signal. The second way of connecting our device is to create a hotspot using the Wi-Fi dongle which is supplied with the VEO Plus. To generate a hotspot, we have to go back into the Wi-Fi configuration page. We need to select Create an Access Point. We can now see the name of the generated network, the password and the associated IP address. Every time we press Generate, a new password is issued to the network. We can now connect the computer to the generated hotspot. To do so, in the Internet Access tab, we select the hotspot network name. Ours is VEO Plus-E202 and write down the generated password. As you can see, I'm now connected to the hotspot. Once connected to the hotspot, we can connect our device using the UT-Link with the new IP address that has been generated. At this stage, I enter the new IP address, which is 10.42.0.1, using the same password and simply pressing connect. I have now taken over the control of VEO Plus with this new IP address. We can now validate our connection status in the About window under the Network tab. It is clear to see that the Wi-Fi IP address has been changed to the hotspot address. The third way of connecting the device is mostly used in places where there isn't any network or the networks are prohibited for safety reasons. In some situations, all electronic Wi-Fi signals must be turned off. To achieve this, you need to go into the Wi-Fi configuration page and turn off the Wi-Fi signal. As you can see, after turning the signal off, the connection between our devices has been broken and the connection status is lost. In this situation, to control your VEO Plus remotely, you must connect via an Ethernet cable. I'm now replacing the connection to the network to the one directly in my computer. The device should again be connected, but I still need a valid IP address to use the UT-Link and the VEO Plus. This connection is not available automatically, so to create a connection, we need to share the computer Wi-Fi connection with the VEO Plus. To do so, you have to click on the Internet Access icon. As you can see, I'm now disconnected from the network. Now click on the network setting in the right list. Click on Status and then change Adapter Options. You should now see your network connection. You can see that your Wi-Fi is disconnected and that your Ethernet 6 is active. In the Wi-Fi property, under Sharing, you need to allow the other network users to connect through this computer's internal connection and then select the Ethernet number 6. When completed, in the About window under Ethernet connection, an IP address should appear. We can use this to connect through UT-Link. You should now be connected using this IP address. We hope this tutorial has been useful. Thank you for being with us.
Hello and welcome to this video demonstration about the new Sonatest FMC TFM solution. This solution is based on the VEO Plus Phaser instrument and the UT Studio Plus analysis software. For the purpose of this demonstration, I'll be using the VEO Plus 3228 PR, a phase array 5 MHz 32 element probe, and a demonstration phase array block. Also, all the screen capture of the instrument in this video have been performed using the XPair software from Sonatest, the remote control solution. Now, starting my instrument, I already prepared a linear scan over the sets of defect. As you can see, we see all the SDHs underneath the probe. Now, because my instrument has the FMC TFM software option on it, I'm able to create a new FMC scan on my instrument. Creating a new FMC scan on my instrument will give me the ability to record all the possible acoustic information under the phase array probe. Now, after setting my travel mode into full time, I can start the acquisition of my instrument. As we can see on the right, I have my linear scan and the defects, while on the left, this is my FMC scan that runs concurrently with my phase array scan. Using a similar dB or gain, we can see that the FMC scan doesn't give much information like a phase array scan. However, with few manipulation to increase the speed, I will be able to record that scan on my instrument. Now what I'm doing is I'm recording over time, but I could also use the record using an encoder. As we can see, I moved my probe over the defect, and now I can save the information on my VEO Plus instrument memory. Now what I'll be using is the file transfer tool from XPair to copy my data file on my instrument directly on my computer for advanced analysis using UT Studio Plus software. UT Studio Plus software is the new generation analysis software from Sonatest for the advanced product. Now, the first view I'm going to introduce you here is the live 3D view. In this 3D view, you see that there is a big red square over the part. What I'm doing with that red square here, this will be the zone where I'll be computing my TFM images. Now, computing my TFM images, I use the LL mode, and I'm computing directly under the probe. By doing that, I'm creating a new set of data files, so a new UT data, having the TFM images in it. Now we can see here on the right that I have my TFM images, but also on the left that I still have also access to my phase array scan. So on the left I have my phase array scan, and on the right I have my TFM scan. And the interesting thing here is that I can compare both defects cut by a phase array and TFM and compare the analysis one side by side. As we can see on the right, the high resolution algorithm down to 0.1 millimeter give high definition about the defect geometries, which in this case are 0.2 millimeter SDHs. Now, to show all the advantages of recording the FMC scan and then recomputing TFM images post-acquisition, I'm going to extend the box or the TFM analysis box to include all the SDHs that were on my calibration demonstration block. So now, using the same FMC scan information that I previously recorded using the VEO Plus, I'm able to compute a new TFM image set using UT Studio Plus, but now over a different zone. I could do the same thing using different algorithm or propagation mode, for example. So now what I'm going to show here is I will apply the same layout, so a phase array scan on the left and TFM images on the right. And the idea here is to show that on my scan on the right, now I see all the SDHs that were not directly under the probe, but that were more on the right of the probe. So if I compare with the other TFM scan or data set that I created the first time, we clearly see that we missed some defect in this zone, while by recomputing a new extended TFM zone, we see that we now include all the defects into the analysis area. Now, an interesting advantage of the Sonatest TFM approach is that all the standard phase array tool like B-scan, TopView, NViews, all the encoded tools that were available for phase array analysis are all available for the TFM analysis. Per example, since I recorded concurrently FMC and TFM, but also phase array scan all together, I'm able to synchronize the encoder together, and then when I get over a defect, I will have the exact same position on the phase array scan and the same signal position on the TFM image. The main benefit here is that the user can use code-compliant phase array to call a defect, but add valuable information from a TFM image. We hope you enjoyed this video demonstration, and if you would like to have more information about the FMC TFM solution or any other ultrasonic NDT product from Sonatest, do not hesitate to contact us at sales@sonatest.com. Also, we remind you that this year is a special year for Sonatest. It's our 60th anniversary. We're pretty proud of it, and we invite you to follow us on the social media, at the different exhibitions around the world, or simply visit our website at sonatest.com.